So we're talking about the Chapel programming language, and like many here, we want HPC to be more open, scalable, and productive. So by open, not only open source, but also open to new people, easier for new people to come in and do something. Scalable, in HPC, we all know and love scalability, getting more performance when you add more resources. And productive, we want new people and expert people to be able to develop HPC software more quickly. So with that goal in mind, let's talk about an example. This is a little bit of an older example, but I like it because it gives you a flavor. So this example is called HPCC Random Access. We can think of it as like a micro benchmark. It's not really an application. So we start out with a distributed table or a distributed array. We're going to be also having a distributed array of updates. And what we're going to do is we're going to go through the updates. And every node is going to be looking at these updates and going and updating memory in the distributed array according to what the update said to do. There's an MPI version of this on the screen. It's too small to read. The red portions are the MPI calls, blue is comments, and then black is everything else. If you look at this MPI code, there's a little comment in the upper corner that says, here's what we want to do. Here's what we want this program to do, and then we've got all this MPI code that sort of implements that on in distributed memory, right? And then our Chapel code for this application is mostly this thing that is on the same magnitude in terms of complexity as the pseudocode that was describing the MPI code. So I really like that story here. And if you look at this loop, we've got a couple of things that like I said, I wanted to give you a flavor of what the Chapel programming language offers. So we've got a for all, that's a data parallel loop that runs in distributed memory on all the cores. We've got a zippered iteration here. This RA stream is a custom iterator. In practice, if you were writing code like this, you'd probably use the standard library. So that's not a really huge amount of code. And then in here inside the body of it, we've got our distributed array access, and then XOR is doing an atomic update to it. Okay, that's cool. So it's nice and small, but how does it perform? Here's a performance graph. This is an older graph from a Cray XC, and it shows the Chapel version is outperforming the MPI version. And the reason for that is that the Chapel version is able to use a compiler optimization to make these atomic updates happen more efficiently. All right, so that's a little bit of a flavor of what our Chapel programming language is about. So I'll go on to introduce it a little more in a different way. So it's a language designed for productive parallel programming, particularly on large-scale systems. It's easy to use. So here I have a little quote from Professor Eric Laurendeau, who's a professor of mechanical engineering at Polytechnique Montreal. His academic group went from, I believe it's C and Python, with MPI to Chapel, and he says, we ask students at the master's degree to do stuff that would take 2 years, and they do it in 3 months. So for his group, switching to the Chapel programming language was a huge benefit in their velocity. It's portable, runs on different kinds of HPE supercomputers and clusters, other brand InfiniBand clusters, Unix systems, laptops, NVIDIA and AMD GPUs. It's fast and scalable. Here I have a result about achieving about 8.5 terabytes a second, sorting 256 terabytes in 30 seconds or so on 8,000 nodes of a Cray EX. And my favorite thing about that number is that the Chapel program that did that is about 100 lines long. It's GPU ready. We have real-world applications that were ported onto GPUs with a few changes and have been run on leadership systems like Frontier and Perlmutter, and it's open source. We're Apache 2 licensed, we're on GitHub, and we're accepted into the High Performance Software Foundation by the TAC. I'll get to that more in a minute. And then I'll have a QR code with our website at the end. Okay, and then I have one more thing about this sort thing. The sort that I was talking about here that was fast and scalable, this is a, what? Oh, okay. This is a sort from the Arcuda data analysis framework, and recently I was doing a comparison of that same sort algorithm between Chapel, OpenSHMEM, and MPI. And so like I was saying, we're proud of that sort being pretty small in Chapel, but it's also actually faster than what I was able to implement in OpenSHMEM and MPI. So if you're interested in these distributed memory programming models and you want to play and be in some of my charts and things like this is also an open source thing where you can add another implementation. Here's a chart with a bunch of users of Chapel. I'm going to focus in on 3 of them. These users of Chapel go across a bunch of different domains. We have CFD, image analysis, data analysis. Their sizes are very different. Some of them are just doing work on desktops, some of them on HPCs. We have a blog series interviewing our users. I'm not going to read the quotes for time right now, but you can check that out from our website. As to Chapel and HPSF, we have a lot of aligned goals and values. We both want to lower barriers to HPC. We both want to grow the HPC community, enabling HPC development, similarly, working on lots of different hardware and being portable, and provide performance as well. I have a quick, I'll just run through this really quick, some information about where Chapel runs. We have some ways to run it in the browser, on laptops, HPC systems. It can run on AWS, probably other cloud providers. Works on lots of CPUs and GPUs and networks. And then getting to the part about Chapel and HPSF, we are accepted as an established project by the Technical Advisory Council as of January. We're in the process of taking steps to fully join, including making some of our meetings public, documenting our project governance and technical charter. We've got a new website. If you haven't looked recently, we've had some public design discussions, and we're still working through some of the legal details to kind of complete the process of joining. So Shreyas and I look forward to meeting many of you this week and learning about what you're doing and how we can collaborate. And I'll put up the QR code and then go on to questions. Thank you.
So we have time for one quick question while our next speaker sets up the next computer. Question? Yeah.
Do you have any case study of Chapel programming which kind of scales across the maybe exascale kind of level systems? Any case study?
Any case study of?
Which scales across application, or which might scales beyond, like up to the exascale?
A case study that scales up to exascale?
Yes.
I think that number I gave of 8,000 nodes is pretty much the biggest we've run on. Oftentimes people record cores, but that's a pretty big amount of nodes. Those are relatively new nodes.
Okay, thank you.
Thanks again.